So last week we learned how to name binary ionic compounds. These were type 1 ionic compounds where it was a fairly simple set of rules to come up with a compound name. Today we're going to take those rules and add just one more thing to them to name type 2 binary ionic compounds, or BICs, where we're using transition metals. So a quick review of those previous rules. We know that a binary compound has two elements, and it's ionic, which means there's a cation and an anion, one with a positive charge and one with a negative charge. To write the names, first you name the metal simply as the element that you see, and then you name the nonmetal where you replace the ending with "ide" or IDE. For example, NaCl, we have the cation sodium, which is the positive charge, bonded with the anion chlorine, which is the negative charge, becomes sodium chloride. Or MgBr2 becomes magnesium bromide. One thing to notice here, the +2 charge becomes the subscript for the bromine. That's something to keep in mind when we kind of flip this concept around, and instead of taking a formula and writing the name of the compound, we take the name of the compound and use that to write the formula. So here's a flow chart for naming type 1 binary compounds. First you look at the metal. The metal will be the first element present. You say, is it a transition metal? So by transition metals, we're looking at something that comes from this section of the periodic table. If there's a transition metal present, then we'll talk about those rules today. If there's not, you simply name the metal and then change the ending of the nonmetal to "ide." There are a couple exceptions to the transition metal rules that we're about to learn. The elements silver, cadmium, and zinc. These follow your type 1 rules, even though they are found in the transition metal area of the periodic table. So naming BICs with transition metals. Problem comes with those metals, because these metals can have more than one oxidation charge, with becoming more than one different ion. So we need to figure out their charges and then somehow convey what their charge is in that particular compound, keeping in mind that the total compound must be neutral. So that means we have to have the same number of positive and negative charges. In order to figure that out, we're going to use the nonmetal to determine the charge on the transition metal ion. So our first example is CuO. What we have here is a compound made of copper and oxygen, copper being a transition metal that can have more than one charge. Oxygen, the nonmetal, only has one possible charge. So in order to find the charge of copper, we're going to use the charge of oxygen. Oxygen is a -2. Think now about what you would have to have in order to make this neutral. How many positives would you need to make this balance out to be 0? Of course, that means you would need +2. So copper has to be a +2, which makes the name of this compound copper 2 oxide. We use the Roman numeral for 2 to indicate the transition metal charge. Here's another example. In this compound, we have cobalt bonded to chlorine, and notice we have 3 chlorines to work with. So first we figure out the oxidation charge of chlorine, and that would be -1. There are 3 of this element in this compound, so a total is -3. For cobalt to balance that out, cobalt has to be a +3, which makes the name of this compound cobalt 3 chloride. Looking at another example, again we're using copper, and this time it's bonded with sulfur. Something to note here, in this compound there are 2 copper ions. So we're going to write each ion giving it a plus something. We're not totally sure what the positive charge will be for each ion, but they will be the same. And then we look at sulfur. Sulfur has a -2 charge. So to balance out the -2, copper needs to have a +2, but since we already have 2 of them, this would get a +1, and this would get a +1. That makes this compound name copper 1 sulfide. Our next example, Fe2O3. Each oxygen is -2, and we have 3 of them. So that gives us a total of -6. To balance that out, our ions must be a +6. Since we have 2 irons, each of them is a +3. So you can see that we have to do a little simple math in order to figure out the charge on the transition metal. That makes this compound iron 3 oxide. Let's take a look at these compounds. Now we're starting to get into the issue of naming binary ionic compounds, but for these 7 examples, you have to remember whether you're dealing with a transition metal or not. If we just scan through them, I know that potassium and sodium are not transition metals. So at least these 2, maybe more, will be named with our previous rules of simply name the metal, name the nonmetal, add "ide" as the ending. The others, oh, here's another sodium. The others, this is chromium, scandium, and lead. Those are transition metals. So let's take a look at how we name these. KCl, simple, potassium chloride. Na3N, again, not a transition metal, so sodium nitride. Just something to note, since there are 3 sodiums, that means the nitrogen in this has to be a -3 to balance that out. That'll come in handy when you learn to go backwards from compound name to formula. CRN. Okay, so here we get our first transition metal example. Cr is chromium. We're not sure of the charge on chromium. It can be one of a variety of things. We know the charge on nitrogen is -3. It will always be -3. So to balance that out, chromium has to be +3. So the name of this compound is chromium 3 nitride. Sc is scandium, and P is phosphorus. So to do this particular problem, we have to balance out the subscripts. We have 3 scandiums. We're not sure what their charge is yet. We have 2 phosphoruses, and we know the charge on phosphorus is -3. So a -3 and a -3 is -6. That means our scandium has to total a +6, which makes each ion a +2. So that makes the name of this compound scandium 2 phosphide. Moving on. The next compound is PbO. Pb is lead. Oxygen is a -2. To balance that out, lead must be +2. So we have lead 2 oxide. The next one is PbO2. We've added another atom of oxygen into the compound, so we need to change the charge on lead. In this case, we have -2 and -2 gives us a -4, so lead must be lead 4 oxide to balance that out. Next we have Na2Se, so we're dealing with sodium and selenium. Sodium is not a transition metal, so regardless of the charges of each of these, sodium selenide is our compound name. Just so you're aware, selenium has a -2 charge. This is why there are 2 sodium ions in the compound to balance that out. So here's a review of our rules. First, you ask yourself, is there a transition metal present? If not, name the metal, name the nonmetal, add the IDE ending. If there is, name the metal, figure out the charge, add your Roman numeral, and then name the nonmetal with the IDE ending. So here is a quick review of what we've just learned.
This is an introduction to naming ionic compounds with transition metals. The transition metals are the elements in this part of the periodic table, and when we write the name for an ionic compound that contains transition metals, those names usually have Roman numerals in the middle of them. So in this video, we'll learn how to take the formula for a compound that contains a transition metal and how to write the name for it with Roman numerals and everything. So transition metals. The transition metals are the elements in this part of the periodic table here, and I've written in some of the most common. I'm also going to be talking about some of the metals over here, which aren't technically transition metals, but they act a lot like them. These metals are unique because many of them are able to make multiple ions with different charges. So iron, Fe, for example, is able to make an Fe2 plus ion, but it's also able to make an Fe3 plus ion. Okay, this is different from the metals, say, over here, that tend to always make ions with the same charge. Sodium, for example, is in this +1 column here. And so when sodium is in an ionic compound, it always makes an ion with a 1 plus charge. Magnesium here is in this 2 plus column, so when it is in an ionic compound, it makes a 2 plus ion. But the transition metals can make a wide variety of different ions with different charges. Some of them can even make 4 or 5 different ions, each with a different charge. So these different charges on transition metals really come into play when we want to name a compound that contains a transition metal. So here we have FeCl3. And for the Fe, the iron, we can't tell right away, just by looking at this, whether the Fe is Fe2 plus or whether it's Fe3 plus, right? We have these two different types of ions that Fe can make. Now, we can distinguish between these two ions by using Roman numerals to give them different names. So the Fe2 plus ion, we call that iron 2 with the Roman numeral for 2 in parentheses. The Fe3 plus ion, we call that iron 3 with the Roman numeral for 3 in parentheses. And we'll use these ion names when we want to name the whole compound. So if the Fe here turns out to be Fe2 plus, we'll call this compound iron 2 chloride. And if this iron is iron 3 plus, we will call the compound iron 3 chloride. So in order to figure out whether we're talking about iron 2 chloride or iron 3 chloride here, we got to do a little bit of math and work backwards to figure out which of these two charges iron has in this particular compound. Let me show you how to do it. So to find the charge of a transition metal, we start by focusing on the ion with a charge that we do know, that's certain, that's not going to change.
Something to note here, I just want to point out, this particular screenshot of the periodic table and the charges that go with each group, this might be something you want to take a screenshot of and keep in your files to use for future assignments, because these are the elements that you'll be working with and the oxidation numbers that they have. So you know that these particular oxidation numbers are consistent. The other thing you can do is label a paper copy of a periodic table so you know which elements have which oxidation numbers. This means you don't have to go back and figure out the oxidation number for each particular naming example that you come across.
And for this, that's going to be Cl. Cl is in this column here on the periodic table, so that we know that in an ionic compound, Cl always makes an ion with a 1 minus charge. Okay? So we've got Cl1 minus. Now, how much total negative charge do we have here? We have 3 Cl's, so that's going to be 1, 2, 3. And since we have 3 of them, the total amount of negative charge is going to be 3 minus. Now, in an ionic compound, the negative charge always has to balance out with a positive charge. So if we have 3 minus on this side, we've got to have 3 plus on this side. So what's the charge on iron now? Well, there is 1 iron ion in this compound, which means that all of the positive charge has to be on this one ion, which means that its charge is Fe3+. Okay? So one ion of Fe3+ gives us 3+ of charge, which has to be balanced out by the 3- over here, which is distributed over the 3 Cl-. So that's how we figure out the charge on iron. And since this is iron 3+, the name for this compound is going to be iron 3. And then for Cl, when chlorine becomes a negative ion, we call it chloride. The IDE usually gets added to the name of an element when it becomes a negative ion. So chloride is what we call Cl1-. So iron 3 chloride is the name of this compound. We had to work backwards and figure out the charge of iron, and then we can call it iron 3. So if you want to get really good at naming compounds with transition metals and using the Roman numerals and all that, you just got to get a lot of practice. So I made another video that's just a whole bunch of practice problems on naming ionic compounds with transition metals. But before you check that out, I want to talk about a couple of important things. The first thing I want to talk about is when we use Roman numerals for naming and when we don't. This confuses a lot of students, okay? So when do we use Roman numerals? Well, we use Roman numerals when we're naming compounds that contain transition metals. So here are 3 compounds that contain transition metals, and as you can see, we use these Roman numerals. And we use the Roman numerals because copper, iron, and vanadium are transition metals, which means that they can make multiple ions with different charges. So we kind of need to pin down the specific ion that we're talking about in each one of these compounds, right? So we put this 1 here to say we're talking about copper 1+, because copper could make other ions. We're talking about iron 3+ here. We're talking about vanadium 4+, because they could be a variety of different ions. Now, on the other hand, we don't use Roman numerals when we're naming compounds that don't contain transition metals, that contain, for example, the metals over here. Take potassium iodide, for example. Potassium, K, is in this column. It's in the 1+ column, which means that in an ionic compound, potassium always makes an ion with a 1+ charge. That's the only choice. It can only be 1+. So we don't need to put a Roman numeral in there to specify that it's 1+, because that's the only choice that it could be. Calcium nitride over here, calcium is in this 2+ column, and it can only make an ion with a 2+ charge in an ionic compound. So again, we don't need a Roman numeral to say that, because there's only one choice, and that's 2+. Now aluminum over here can only make a 3+ ion, so you don't need to use Roman numerals with aluminum either. And I should point out that some of these metals here that are not technically transition metals still can make ions with different charges, so we have to use Roman numerals when we name compounds with tin and lead in them as well. But here's the big point. If you're naming compounds with ions that can make different charges, you always need the Roman numerals. But don't put those Roman numerals in if you're naming compounds with metals that can only make 1 charge. Not only is it a waste of time to put those Roman numerals in, but it's wrong. You just shouldn't put them in there. Now we have to use this method of working backwards in order to name compounds that contain most transition metals. And we also have to use this method to name compounds that contain metals like tin or lead that are able to make more than 1 type of ion. But there are 2 important exceptions that I need to tell you about. And these are silver, Ag, and zinc, Zn. Even though these 2 elements are transition metals, they're only able to make 1 type of ion. So silver, Ag, always makes Ag 1+. It's always 1+ and only 1+. Zinc, Zn, always makes an ion that is Zn 2+. Now, that means that when we name compounds that contain silver or zinc, we don't have to use Roman numerals because we're only talking about 1 type of ion. Okay? So a compound like this, AgCl, you don't have to do any math at all. You don't have to use a working backwards approach. You just call it silver chloride. ZnCl here, super easy, we just call that zinc chloride. And since these elements always make ions with just one charge, we don't have to use the Roman numerals when we're naming them. So it would be wrong to call this silver 1 chloride or zinc 2 chloride here. There's only one possible ion, so we don't use the Roman numerals. We only use the Roman numerals if we're trying to distinguish between multiple types of ions with different charges. So that's an introduction to how we name compounds that have transition metals. In the next video, we'll do a whole bunch of practice problems so you can really get the hang of it. This is one of the things that you just get better and better at with more practice. So check out that video. You'll get super good at it really fast.
So that gives you a good idea of the elements that you'll be working with when you name compounds with transition metals.